shows you the trend, okay? Increasing alpha cellulose, decreasing DP with hydrochloride, which we refer to as chemical bleaching. Then the impact of chemical and bio-bleaching on alpha cellulose, degree of polymerization, and tensile strength. In table 3, I simply want to show you in terms of the virgin craft insulation paper, again, according to literature, we see about 90% alpha cellulose, and if you look at if you look at the eight craft insulation, we get 66.7 in terms of the alpha cellulose, and then you can see the degree of polymerization is dropped. I am showing you the physical strength, the physical parameters of tensile strength, stretch, and the tensile energy absorption. So again, here you can see decreases. Okay. So with the age, there are obviously decreases with tensile strength, stretch, and the tensile energy absorption. So you can see that despite there's a decrease in tensile strength, stretch, the minimal levels are not below the threshold limits for its end of life as an insulating paper. I want to indicate that means while there's a decrease in alpha cellulose, while there's a decrease in the degree of polymerization, tensile strength, stretch, and the tensile energy absorption, craft insulation paper can still carry out its insulation properties at these levels. So it's not in a bad state, it's not in a critical state as such. Okay, so if I look at the chemical and physical parameters of rejuvenated in table 4, so what is shown here is now we've taken the aged craft insulation paper and we have basically exposed it to chemical bleaching, again, as you would see, A, B, and C, and here we've chosen, in terms of A, B, and C, we've chosen 1.2% of hypochlorite and peroxide concentrations, 1.5 and 1.8. And this was basically born out of the previous, the previous experiments where we found that this would give us the best chemical bleaching effects. What you need to know in table 4 is the bio-bleaching D actually gives us very high alpha cellulose. It gives us again a good degree of polymerization. The tensile strength, the stretch, and the tensile energy absorption are all well above the threshold. Okay, so you can see that in this kind of work, the bio-bleaching seems to be coming out as an effective, or if not, basically doing its job in rejuvenating this paper. So previous scientists have benchmarked insulating paper that has reached 50% of its original tensile strength to undergo severe degradation. So remember I said that we're looking at chemical and physical parameters. This is in insulating paper, insulating oil, we have so many parameters to deal with. But sometimes we look at the sort of main parameters that we could deal with. And in this case, for example, tensile strength becomes an important parameter. And hence we can see here, for the chemical bleaching, the tensile strengths have decreased quite a bit. But in terms of bio-bleaching, it's held its value at a very high value. And that is a sort of a marker, a flag to say that the bio-bleaching can work. Okay? So bio-bleaching, the lowest change in tensile strength, stretch relative to bleaching, as you can see, I've shown that in table 4 highlighted in red. So biological bleaching produced rejuvenated, which I call it bracket, aged craft insulating paper with the least negative physical and chemical alteration. Okay? And again, the change in tensile strength and stretch as a measure of thermal aging, chemical and biological bleaching. So I'm showing you basically again, if you look at the change, so table 5 is just showing the change. And just to highlight on the bottom, you see in table 5 that the bio-bleaching has undergone the least changes in terms of tensile strength, stretch, and your tensile energy absorption. In table 6, Basically, what we did was we looked at the mass balance of material, and when we looked at percentage of material loss, remember, you're oxidizing. So again, D highlighted in red, table 6 simply shows you percentage of the original paper remaining, of the eight craft installation paper, and the percentage of material lost. We quantified the 2000 by high performance liquid chromatography, HPLC, and again here you can see virgin craft installation paper and comparison between age. Obviously there's a loss in tensile strength, and you can see the increase in the 2000. Okay, so there is an inverse proportionality between 2000 and the tensile strength. So in table 8 we basically show this. Again, I just want to highlight in table 8, with chemical bleaching versus bio-bleaching, we have basically a 2000 of 12.54 ppm compared to a very high 2000, which means that you've got higher degradation of the cellulose or the cellulose units to give you the furanic acid components. And again, the tensile strength holding its value to give us a good quality. We looked at the crystallinity index, and in terms of our crystallinity index, again, I don't want to take you through too much of the discussions, but here we see that the bio-bleaching showed a higher crystallinity index. And basically, crystallinity index, I know many of you are experts in this, highlights changes of the morphology of the cellulose which occur during bleaching. So, to a certain extent, the bio-bleaching has not disrupted the morphology of the paper, and there still has to be quite a lot of work done on this. I didn't delve too much into this kind of work. And when we measured the crystallinity index, again you can see bio-bleach on the top at the bottom, shown in table 9. And finally, when we looked at surfacing image, so we tried to delve into SEM, and it's always a difficult scenario to look at SEM images. But here simply what we were seeing is that the crystallinity, rigidity, and flexibility are the key properties of fiber morphology. And when you look at the pivotal role it plays to function as an insulating effective material, so what happens during aging and bleaching? You get an alteration of the structure of the fiber, and a flattening effect of the fluting was observed for the aged craft insulation paper. And so if you look at the images, A is virgin craft, okay, so A at the top here, you can see B is A, so in B you can see the flattening effect. C is bio-bleach. Image D, okay, you can see, image D again has a flattening effect, and basically with the peroxide, there's not so much of flattening, but hypochlorite and thermal aging basically shows that flattening effect. So from the images, the raised flutings and chopped furrows were clearly visible as a result of thermal processing to achieve the creep effect. In other words, we have what we call thermally upgraded paper, and you can see the flutings, or what we refer to as the flutings and chopped furrows, that basically was thermally processed to what they refer to as crepe effect, to enhance the thermal stability of paper. But just to show you that you get the flattening when you age this particular paper. So in terms of the conclusions, chemical and bio-bleaching was successful and effective in treating accelerated age virgin craft insulation paper. Chemical bleaching worked in certain bleaching trends. Bio-bleaching using the actinizo spray tube proved to be the best suited rejuvenation technique, since it generated the highest percentage of the cellulose and obviously gave us acceptable clear polymerization. The chemical bleaching techniques require careful and controlled cleanup treatments, as they are chlorine and hydrogen peroxide-based reagents, while bio-bleaching is an extremely eco-friendly technique. And I've just listed the optimum conditions that were attained. And finally, the 2000 Mahavidyalaya is an important marker in identifying degradation of the virgin craft insulation paper. So I would like to pass my acknowledgements to the School of Agriculture and Science here at the University of KwaZulu-Natal. ESCO Tertiary Education Support Fund, the NRF, PhD student Dr. Yashmika Jion, our lab technician Mrs. Anita Naidu and Mrs. Kunati Bongoza, and my colleague from Johnson Lynn School of Microbiology. I would also like to thank the organizers of the International Conference on Bridging Disciplines from Chemical Sciences for a Sustainable Future, Dr. Amrit Mitra and Dr. Neha Rao for extending an invite and for the information shared, and to all you delegates and participants for your attendance and participation. Thank you very much.
Thank you so much, sir. It seems something new is going to come with insulating papers, and it's so good to see that such intensive research is being carried on by fellow Indians all over the world. Now we have another online expert joining us, Mr. Professor Brijesh Pare, and I'm honored to introduce him. His qualifications are MSc and full PhD postdoctoral fellow, and he has been the president of Association of Chemistry Teachers in India from 2020 to 2024. Presently he is in the institution Madhav Singh Postgraduate College.
Thank you. Are there any questions?
Any questions from the previous expert? Viseshwar sir, Ajay Viseshwar sir, any questions from the audience? Sir, no questions. Thank you so much, sir.
Thank you very much. Have a good day.
Thank you, sir. I'll continue with Dr. Brijesh Pare's introduction. He has more than 90 research papers in various international and national journals of repute. He has given research guidance to 21 PhD students. 6 students are still registered and working actively under him. He is the IUPAC member, INSA nominated affiliate membership of IUPAC UNESCO 2012-2013. He has coordinated more than 150 chemistry popularization workshops for students and teachers across India, Abu Dhabi, Dubai, Sharjah, and Doha. He is the panel member for National Level Best Chemistry Teachers Award instituted by Association of Chemistry Teachers and Tata Chemicals. His research interests are advanced oxidation processes, photocatalytic degradation of organic pollutants such as pesticides, dyes using UV and visible light, green chemistry and sustainable science. He has been engaged in doing extensive work on training programs for learning and teaching creativity using various models. Students at every level need a creative and flexible mind for learning and integrating new knowledge. So he has been cultivating.
I am not able.
Yes. Yes, you are audible. So he has been cultivating young learners' creative capacity in order to be well prepared for study, work, and personal life. He is working on all levels of teaching and learning phenomena-based learning. His topic of interest are atomic structure, organic reaction mechanism, chemical kinetics, quantum mechanics, thermodynamics, green chemistry, spectroscopy, etc. As a research person in various literature and orientation courses for teachers. He is the referee for Refer Journals, Journal of Physical Chemistry published by American Chemical Society USA, International Journal of Colloids and Services Company, and Alzheimer's Science from Netherlands, International Journal of Chemical Kinetics published by Wilfred USA, Science Education Review, Queensland, Australia, Lane Group Chemistry Taylor and Francis Group, Oxfordshire, UK, European Journal of Chemistry, and International Journal of Ethiopia, Journal of Hazardous Materials, Alzheimer's UK, Indian Journal of Chemistry, CSIR, Library, Journal of Indian Chemical Society, Kolkata, South African Journal of Africa. He has got the membership of chemical associations. He is the president of Association of Chemistry Teachers during the period 2020 to 2024. He is a life member of Chemical Research Society of India, Indian Institute of Science, Bangalore. He is the life member of Indian Council of Chemists, Agra. He has been awarded postdoctoral fellow at the National Research Foundation, Pretoria, South Africa, for 1 year between May 1999 and 2001 at University of Durban, West Bengal. INSA nominated for PhD membership, IUPSA UNESCO 2012. Today he is sharing his results in sustainability circular chemistry. We welcome you, sir.
Thank you, madam. I'm audible?
Yes.
Okay, and I have shared it. My presentation is there. It is visible. Okay. Let this start. Don't stop. Sorry. Yeah. Okay. Thank you so much. And good morning, the principal, Navyug Kanya Mahavidyalaya, Lucknow, Dr. Neha Agrawal, the organizer, the convener of the program. The professor given the from University of Durban, Westville, University of course, the child, he is attending the program, my teacher, then Professor Ramesh Yanga, and all the organizing members of this wonderful national conference. So, thank you for giving this opportunity, and I have been given sufficient time to speak on circular chemistry. I'm with this, we are talking about sustainable development, and Dr. Neha has really chosen a very apt title for it, and this is really a time, on the chemist to talk about how we can contribute for sustainable development. We are all aware of the 17 sustainable goals in everywhere we are talking about, and what is the role of chemistry to have a sustainable development on the planet. So just one thing, I used to say, spending beyond income, makes us bankrupt. So consuming endlessly on the finite earth can make us suffer miserably. That is what is happening, because we have exploited our earth to a very huge extent. What has been doing for the last so many years, immediately after the industrial revolution, like we are taking resources, extraction is done, things are manufactured, goods are manufactured, distributions have been carried out, consumption is done, and after the use, the particular goods or material has been thrown to the landfill, and that is a kind of a waste. So this is a very linear approach, all we have been doing so far. But now the time has come, that the role of chemistry has to come on the fore, and a lot of work has been done, across the globe. So the circular chemistry is very important these days, and just by expanding the scope of the sustainability to the entire the life cycle of chemical products, the concept of circular chemistry aims to replace the today's this linear, what just I have spoken, take, make, and dispose approach with the circular process. That we need to learn from the nature. And this will optimize resource efficiency across chemical value chain and enable a closed loop, waste-free, chemical-free, just to save the planet. Yeah, this is our scope. So now, everything is really very important. Just to know the finite nature of the resources, including the elements, scarcity, we understand so much of lithium, so much of elements we are using, throwing to the landfill, and as well as the limited environmental requirements to few decades. So now the time has come to us to contemplate it and what more can be done and what can be done. So circular chemistry has really come to rescue for this. It's really helpful, obvious that the linear route of production, in which the most of the precious and important and scarce limited resources are consumed and their value-added products are degraded to waste. Okay, and that is the root cause of several impending global crises. We talk about climate change, diminished biodiversity, as well as food, water, and energy shortage. So this is the source, this is the root cause of all these kind of problems we are facing. And this is just one, like you might have seen, in this, the periodic table, the kind of the elements diminishing, and that is a one-time resource, we cannot have it, again. So now the circular, now for to attain a sustainable development, circular economy is very important. So what is the circular economy? Circular economy is restorative and regenerative by design and aim to keep products, components, and the materials at the highest utility and value at all times. Highest utility and value at all times. That is the definition of circular economy. And chemistry is crucial for achieving this. This is here comes the role of chemistry in order to enable circular economy, thereby saving the planet, thereby attaining the sustainable goals. Yes, sir, just brief about what is the restorative and regenerative design. So the restorative and regenerative design focuses on creating systems that are not only minimize harm to the environment, but actively restore and enhance ecological health. That is a wonderful thing. Not only we are minimizing the environmental health just by having this circular economy, but we can restore the ecological health of our planet. And again, the role of chemists. Chemists understand their role in designing and developing indispensable materials and technologies, but also simultaneously recognize the potentially detrimental effects. Chemists are aware that each state must be designed and reassessed with sustainability in mind. That is very important. Lots of things are happening, lots of new materials are coming, lot of new technologies are coming, but now the time has come that we have to think beyond the green. Even if the process is green, it has to be tested whether it is sustainable or not. I will give you few examples of that. So green chemistry last 25-30 years have been practicing. We all know about the 12 guiding principles of green chemistry. They focus on the direct sustainability assessment of the chemical reactions and are perfectly suited for the optimization of linear production routes. Okay, that is fine. Green chemistry has contributed enormously for optimization of linear production. The developments towards a circular economy, however, require a re-evaluation of what defines a sustainable chemical process and needs to take into account three things: the people, the planet, and the profit. These three criteria has to met, in order to prove that the process is sustainable or not. Usually it is called a triple bottom line. We probably all aware of it. So innovative chemistry design with sustainability in mind is only effective when translated into economically viable applications. Because see, the growth, the development cannot be denied. We have to go ahead. The society has to go forward. We need to synthesize new material every day. The technology has to improvise, but every time for every kind of reaction, the chemist does any kind of the invention or innovation is done. These three things have to be taken into mind: the people, the planet, and the profit. I will give some examples. So the chemistry of sustainability, or you call a sustainable chemistry, that recognizes that sustainability without innovation is impossible, and innovation without sustainability would be ruinous. So this is a punchline, that is really in order to have a sustainable world. These are the 12 principles of green chemistry. I am not going into the details. We even at every level, even undergraduate and postgraduate level, we have all just gone through it a number of times. but I'm not going to read out all these things. I will just we'll go towards the sustainability. Green synthesis of hydrochloric acid, for example, so which is a key component of the manufacture for nylon 66, and it is done by the direct oxidation of cyclohexene with hydrogen peroxide. Okay. Now this reaction, that is cyclohexene and hydrogen peroxide, is solvent-free conditions because nitric acid is not being utilized here, and thereby the environmentally taxing gas like nitrous oxide doesn't come into play. So it's a green matter. But and it requires hydrogen peroxide, which is a green oxygen. It's a starting material. So this whole thing, that this reaction is a green reaction, it is a green matter. Now, the problem with this, that the hydrogen peroxide is more expensive than the adipic acid, which is a product. You're getting my point. So now this is not commercially, industrially viable because it doesn't fit to that PPP, the planet, people and profit. Yeah. So although this route obeys the green chemistry, but it violates the value chain. So as a result, this green adipic acid synthesis has not been applied industrially and therefore not led to an overall increase in the sustainability. So every time, this is one example where there is a need of accounting the profit level of that triple bottom line is very essential. One more example let us have, which we all know, that is a Haber-Bosch process, and this is an example of clean chemistry principles, where it is economically viable, okay, but still not sustainable. Why? Because see, here what is happening, iron is being used as a catalyst, nitrogen and hydrogen making ammonia, which in turn used for the production of agriculture fertilizers. It is a key industry showcase for the use of catalysts because iron is being used in increasing energy efficiency. The current process requires high temperature and pressure, and further optimization has stagnated. Okay. Moreover, like see, despite being a catalyst is used, okay, it is economically viable, but it is a problematic thing. See, what is happening? Eutrophication. After the use as a fertilizer, large portion of the fixed nitrogen, they are lost to the environment, causing eutrophication. It's a global environmental concern, and the importance of it should not be underestimated. So an increase in water and air pollution, both of which threatens to destabilize the Earth system beyond the proposed planetary boundaries and safe operating space for anthropogenic activities. So this highlights the importance of looking beyond the scientific discovery. See, the reaction looks to be quite viable, economically viable also, but it is creating a lot of troubles like eutrophication. Therefore, it cannot be considered as a sustainable reaction. So now the time has come, the importance of looking beyond the scientific discovery and analyzing the global impact of chemistry using a systems approach. That is very important. These two examples, just giving a glimpse of the things, like how they both are green reactions, but at the same time, because of different reasons, they are not sustainable. Circular chemistry for sustainability. So this, particularly today's my talk, that one of my friends, Jay Chris Stoopmate, they are working on it from Netherlands, and I have just given the reference of the paper also, and they are working hard on it, Now the closed loop waste-free chemical industry. This approach aims to make chemical processes truly
This meeting is being recorded. This meeting is being recorded.
That, instead of the microplastics. So that should be the option. So that is what the circular chemistry is trying to do, and that energy input is an investment. This is something very important because from early times we talk about the recycling, but recycling is consuming so much of energy, and so energy must be taken into consideration. So using waste as a resource can also contribute considerably to the energy efficiency of a chemical product over its entire life cycle. So in order to repurpose waste material into a feedstock, it is important to achieve a recirculation of molecules and materials that ensure an energy economy. For example, carbon dioxide can be converted into a variety of molecules like even alcohol or methane, and which can in turn be used for a variety of purposes. But the conversion of the process should not necessitate more energy than that offered by the product often. Okay, this is very important. Conversion is fine, that CO2 can be converted into alcohol or methane or even amines, but the energy bookkeeping has to be taken care of. Yeah, that is there. This emphasis on the reusability of materials means that their longevity, which requires they remain chemically stable over many product cycles, is valued over their degradability. Because what the green chemistry says that the product has to be degradable. Instead of the circular chemistry, it the plants, that it has to be more stable chemically. The product, okay, yeah, because sometimes the degradation may not be very good. So by building the energy stored in the material as a long-term investment, circular chemistry aims to conserve energy and thus reduces additional energy inputs. Something that is very important. Controlled environment is another thing. The inherent reactivity of chemicals enables their conversion into value-added compounds, but can also lead to adverse effects. So in a similar manner to green chemistry, the circular chemistry strives to reduce the harmful impact of these compounds on the environment. Although the use of substances of concern may be unavoidable at some facilities, these should not be released to the environment. This is the thing, that even if suppose a very high toxic chemical is there, some material is there, so the effort has to be made that that should not be released to the environment. That is the CC6, that is the circular chemistry principle 6, that it should not go into the public, it should not go to the society. This approach requires the continued conglomeration of industrial sites and enhanced cooperation between the companies. That is what is, these days the industrialization are done, that on one place there are a big industry, but there are cluster of, related industries are there, and they combine in a manner so as to reduce the energy consumption, so as to reduce the requirement of the energy, just supporting each other. So that is where we can go to the sort of circular economy, that is one of the things. Product design. Optimal product design should target the most end of life stage, avoiding persistence in the environment and breakdown into harmful. This is another important thing. You suppose the product has to be designed in such a manner that just by getting, after use, it gets degraded and creating harmful effect to the people around, to the society. Rather, it should be designed in a manner that it should not break, like that. So biodegradable materials is often seen as sustainable. Yet the fact that the product simply be disposed of in environmental promoting. That is what earlier also I talked about, that biodegradable materials are also sometimes they are problematic. Another issue often overlooked is that the microplastics I have just spoken about it. The polymers partially degraded from a plastic bottle causes more harm to the environment. That is. Following the green chemistry principles to encourage chemists to design materials for degradation does not unequivocally lead to an increase in sustainability. Therefore, rather than aiming for product degradation, it is preferable to collect waste streams and instead convert them into dedicated plants that into value-added materials. So degradation should be preferred, should be avoided, and the waste should become a resource for any value-added product. Product stewardship. The circular economy relies on decoupling of material consumption and economic growth. This is something very important because we are in a time when the economic growth is very important. We cannot just go back. We cannot retreat from that, And but every time, we see that if we are consuming more material, so there will be more growth, but we have to have a balance on that. To promote this, the ownership of goods needs to be directed away from the user and back to the producer. Ownership of goods needs to be directed away from the user and back to the producer. This can be achieved by shifting payment model from ownership-based to service-based systems. And examples of this is the use of shared car. Yeah. One example, a very successful example of this approach is one in Egypt. ARB is a manufacturer of electrical appliances who resolved high cost in electrostatic powder coating by collaborating with the paint and coating supplier. One company, Exxon Nobel. So instead of this ARAB buying the coating material per kilogram for their painting operations, the companies devised a process in which expenses were charged per square meter of metal material coated, and the powder waste was returned to the Nobel company for recycling. So these kind of collaboration, and they saved a 20% reduction in coating use. So this is the service-based chemical industry is vital for circular chemistry. Service-based instead of the ownership. Okay, so now I will be finishing because Dr. Neha has asked me for running out of time maybe probably. The later of circularity, let me go for it. What the circularity says, first is reduction, reject, reduce, reuse, redistribute, repair, refurbish, repurpose, remanufacture, recycle, recover, and return. You refer to 11 R's that provide the means by which to assess the end of the life option for the product. And this is how this is the letter of circularity. I think this is enough for today's and looking at the time constraint. So thank you very much. So I'm very much sure that circular chemistry will definitely be in practice very soon. A lot of work is being done on it.
This meeting is being recorded.
Any questions?
Any questions from
The circular economy and sustainability.
Anyway, no problem. You can take a question and then send it to me. No problem.
Okay, sir.
Okay.
So, if you have questions,
And the principal of college, thank you for giving me the opportunity to speak. Thank you so much.
So, there is a query what is how to conduct green audit? Yes. How to go about it?
No, earlier, there was an environmental chemistry where we are making all kinds of waste. We were never thinking of avoiding waste. And once all kinds of waste were made, like air was polluted, water was polluted, and then there were methods of elimination of those kind of elimination of the best air, elimination of best water. But once the green chemistry comes with the 12 principles, almost in 1985, so we have to avoid waste. Yeah, we have to avoid waste. We have to there are 12 principles of that. So green audit is that you are not adding any carbon dioxide to your immediate environment. Because of course carbon dioxide is very much there. There was a time before the industrial revolution, whatever carbon dioxide coming out of the humans and the animals, that was being utilized by plants, so there was a perfect cycle. But now with the industrialization, excess of carbon dioxide is coming. Whenever we talk of carbon, that is carbon dioxide. So anything, any of the activity, any of the action within the campus should not add any extra carbon. That is what you have to look around. Even smaller thing like in the college, whether the light, sometimes there is a habit of the children, just to switch off the lights, not to use the light when you are not in the room. That is, you are just contributing to the planet, But if suppose somebody says, that the energy, that the light, electricity was a green electricity. So what is the harm in using the excess electricity? Because see, if the electricity is generated by coal or oil or petrol, that is not good. But if suppose, you are just using water for that matter, it's a green electricity. So you can use as much electricity as possible. Anyway, thank you.
What I gather from this discourse, it is that restoration and re-engineering mechanisms must be used more and more. We should have closed-end loops, and there should be innovative chemistry, because for sustainability we need innovations, and our innovation should be sustainable too. So to reduce environmental stress, sir has suggested that there should be reuse and reuse of material. Thank you so much, sir. Now I would like to call upon Neha Pandey for thank you. And then we will disperse for just 15 minutes. 15 minutes we will disperse for tea break and then come back again for the next session. Thank you all so much.
Dr. Neha, madam, where is my tea?
So I can
Okay, thank you so much.
Dr. Pari, how are you, sir?
Ajay. Hi, Ajay.
Namaskar, how are you?
Oh, good. Big drop, huh?
I'm so happy to see you. I didn't realize you're going to give a talk.
No, but I do anyway. So you mix with Jay this time. And but Dr. Neha mentioned you to bring me to Lucknow, at least on air.
I would spend half my time talking all the time at the International Chemistry Olympiad.
I'm also a good fit, man.
Oh, no, you want less straight. I mean,
Okay.
really great to see you. And we must chat because I'm doing quite a lot of work on APG and molecular green chemistry. Yeah, I'm not doing work that I do work. Yeah. So when you come to are you visiting us?
Where you are coming to train and which are coming to India, man?
Well, it's a consulate journey and so we have to
It was really tough. It was really tough. So anyway, Dr. Neha is acting, going for tea and all. So Ajay, we'll talk in the evening.
Okay, see you, Professor. Thank you.
Thank you so much.
The recording has stopped.
Thank you, ma'am. Very good morning, esteemed experts, respected principal, Professor Navyug Kanya Mahavidyalaya, honorable dignitaries, senior professors, and all the scholars, students present over here. I am Neha Pandey, and it is my privilege to deliver the formal vote of thanks on behalf of the college and the organizing committee of this wonderful conference. First, I would like to express my deepest gratitude to Dr. Anirudh Balakrishna Patil for his outstanding presentation on structural re-engineering of mesocomposite materials for sensor applications. Your innovative and insights into material science and sensor technology have truly captivated us and broadened our understanding, sir. I would like to extend my heartfelt gratitude to Mr. Ajay Viseshu for his valuable talk on rejuvenation of cellulose-based insulating paper used in high voltage power transformers. Your presentation was both insightful and impactful, sir. Your research on improving critical materials for electrical infrastructure has opened up essential avenues for innovation in this field. A special thanks to Professor Brijesh Parekh for sharing his expertise on sustainability through circular chemistry. Your emphasis on circular chemistry as a pathway to sustainability resonates deeply with all of us, inspiring us to think about environment in new and impactful ways. I would also like to express my sincere thanks to the principal, Professor Navyug Kanya, for her leadership and unwavering support in making this event a success, and our deepest appreciation go to the convener and co-conveners for their hard work and dedication in organizing this international conference. A very special thanks to Dr. Anurima Banerjee ma'am for her excellent coordination of this session and for ensuring everything ran smoothly. Finally, I would like to thank all our delegates, both offline and online, for their participation and insightful questions and making this session truly interactive and meaningful. Thank you once again to everyone involved, and I humbly request all of you to have a tea break and breakfast. Thank you.
I just have one more announcement. We will resume the session after 15 minutes, after tea break. Thank you.
फोटो खींच देना मेरा टायर के साथ में।
फर्स्ट ईयर साइड प्लीज इनकी बैठक
फाइव का यहाँ पे जब अभी आएंगे लोग तो पूछ लेंगे कि फाइव के कितने प्रेजेंटर्स हैं। 4 है, ठीक है।